This is our last week of classes. So there's a few things to note. First off, before we get started. One, as this is the Monday, Wednesday, Friday class, our final is on Wednesday. Final weeks. You can check that out by going to the academic calendar for the 2021 school year. I will send out an email to remind you, but it's on Wednesday. There will be a couple study sessions held by SMACS, student members of American Chemical Association. There's one at 7 p.m. this Wednesday, the 11th. And there'll be, I think, two of them one on Monday and a finals week and one on Tuesday finals week. Show up, get some help. Hopefully they'll help you review. If not, if you don't got time, it's understandable, but maybe there may be some bonus points in for you. But okay, use this week as a chance to get things done. Don't forget you have test number 4 due at the end of this week before finals week. Use it as a chance to do some review. You got the rest of the homework is due this coming Saturday as well. Use this chance to get that done. Please note, grades are not due till like the Monday after finals. So after I get the finals in, get them graded, I'll be able to tell you where you currently stand. If you have some outstanding homework assessments that you can do that could make a difference, I will let you know. So for example, if you're one of the people who are lagging behind in completing the homework, I'll let you know, if you manage to get 50 or 70 or 100 more points, that could be the difference between a C and a B or B and A. Or some people may not be able to do a whole lot if you finish most of the stuff already. Use this chance also this week in lab. Attendance is not mandatory. It's a chance to go over some homework, get some help, may review a bit more. And for those who are missing more than 2 labs, a chance to make up a lab. But if you've only missed 1 or 2 labs, you're probably fine. As soon as some people get some of the remaining assignments into me, I'll be able to tell them where they stand. I think most people in the at least Wednesday lab are doing rather well. There's maybe 1 or 2 people who maybe know where they're at. No, they need to make up 1 more lab. But if I haven't contacted you in Wednesday lab, you're probably having A. It's the people who haven't turned in some assignments or are missing 3 labs or so. Those are where it starts to be painful grade-wise. Okay. So the final. Let's talk about the final. When the final is, we're going to go into the chemistry lab. We're going to take the final in the chemistry lab, but we might eventually meet in our usual classroom first. The final is 70 questions, all multiple choice, which is good, but it's 70 questions, then you have 2 hours to do it. There is a wide variety of questions. It's cumulative. It is ACS standardized exam. So, it is a pain in the ass. However, and there's some stuff that maybe we didn't go over well enough. But with that in mind, what I'm going to spend the next couple of days is trying to show both examples of these questions and review the various topics. Some of this stuff, they'll have worked out for you. Like if you need to find out a molar mass to turn grams to moles to grams, they will oftentimes give you the molar mass of this because you don't have time to be adding up these simple things. You have to be able to utilize them. Yes, maybe there's a lot of equations. You can bring your calculator. I'd suggest you bring a pencil and I'll give you some scrap paper, but that's all you're really supposed to have for that exam. Calculator, pencil, scrap paper. So you don't come in with a study sheet. You don't come in with, so you have to kind of know this stuff. I mind, as I said, there's a lot of equations, but one of the things I want you to understand, the equations shouldn't be the hard thing as long as you understand what it means to cancel units, what it means to cross one unit out and replace it with a new unit. If you can follow that, there's no equation in the world you really need to memorize. You're just watching this unit go into that unit, go into that unit. I'm just converting here to here to here because I know I start here and I see the connections, like what street do I take to get from this destination to this destination. It's not a matter of memorizing the route, but understanding our initial point and our destination, and then kind of like putting it together on the fly, how to get there. But so yesterday I came in, took a look at the final again, reviewed what all we went over in the various chapters, and we're going to go through basically chapter by chapter, just real quick, what each chapter presents. So if you're going through and looking at what did we learn in chapter 1, I'm going to distill this down into the simplest little bits. Some of these bits may play a very little part of the test. Some of these bits may play a little bit bigger of a part, depending. The stuff that will carry on to next semester will probably be represented a little bit greater than stuff that is maybe just a flash in the pan, like properties of light. Like when we talk about turning wavelength into energy, we're not going to talk about that next semester. And so that's only going to be represented as maybe one question on the exam. As opposed to, like, say, molarity, that's going to be a common topic next semester. And so that's actually 2, 3, 4 questions. So that's the idea. Stuff that is super important gets hit at least 2 or 3 times. Stuff that is not as important barely gets covered. But okay. So what I'm going to do, I'm going to talk about each chapter, some of the minor topics, and maybe examples of each kind. So that's just a quick run through of each chapter. So one of the things we learned, chapter 1, starting off. Chapter 1, we learned our simple conversions. This is the thing that's more important than anything, even if it's not asked directly on the test. Chapter 1, we did conversions. Conversions, we did the metric. So make sure you know how to go from nanometers to micrometers to millimeters to meters. If we can't do that, I mean, that's a big thing. For example, the properties of light, just coming back. If you get a number in nanometers and you try to convert that into a wavelength and you use nanometers, you're going to have a tough time, because c, the speed of light, is in meters per second. So in order to cancel out your meters, you need to turn nanometers into meters. So even though I know the equation, I am trying to turn nanometers into inverse seconds. And the constant I have is c, which is in meters per second. So how do I get rid of that? I'm going to need to divide by meters. So if you cannot convert nanometers into meters, you cannot get this problem even if you know the equation. So make sure you know how to do some simple conversions. And then the other real thing we learned about that could come up has to do with accuracy, precision, and significance. sig figs. So remember, accuracy is how close to a known result is our number. If I get an average of 3.5, my average, and the actual value is 4, that's not very accurate. If I got a 3.5 average and the actual is 3.6, well, it's pretty close. Precision has to do with repeatability. I could get 3.5 by having a 3.4, a 3. And a 3.6. Two numbers give us the average of 3.5. Or I could have two numbers of 3 and 4, and the average would still be 3.5. These two sets would be pretty precise. These two sets, not precise, because the difference between those two is a lot bigger. And of course, our significant figures talked about how accurate the number could be reported. If I had 3 decimal points, and I did a number and I multiplied by 3 decimal points, I should get a number that rounds to 3 decimal points. So, though, please note, significant figures will not play a big part of the exam. If that is your struggling point, and you don't, and you would have to relearn that, don't worry so much about significant figures. Learn more about how to do the applied math, like this coming test. This coming test will be a good chunk of the exam, like at least 20, if not 30 questions. So if you can do most of that, you'll be in a good position. Chapter 2. Also, not a ton of stuff from Chapter 2 that we needed to know. But Chapter 2 did a couple of important things. It introduced us to the periodic table. So, if nothing else, know how to read the periodic table. So, know what it means. What's the atomic number? What is the atomic mass? Be able to figure out how many protons, how many neutrons, how many electrons, and why are these arranged by left to right, and why are these arranged top to bottom? Remember, like groups versus periods. How lithium acts like sodium, which acts like potassium, like rubidium. So another thing, as I said, we introduced the concept of atoms and protons, neutrons, electrons. We introduced that concept. What are they? How to recognize them? How to count them? If I said beryllium, let's see, beryllium 8 with a mass of 8. How many protons, how many electrons, how many neutrons would that have? Well, beryllium is element 4, so it'd have 4 protons. Because it has a mass of 8, 4 plus 4 is 8, it'd have 4 neutrons. Because it's neutral, it would have to have 4 electrons. So be able to recognize and differentiate and count that. We learned about isotopes. Isotopes, remember what an isotope is. An isotope is an element that has a different number of neutrons. So we can have chlorine 35 or chlorine 37, 2 different isotopes of the same chlorine. They just have 2 more neutrons between the two. And then we learned very briefly about atomic mass and the weighted abundance. That, for example, because chlorine 35 is 75% of all isotopes, and chlorine 37 is 25%, the weighted average means the average molar mass is 35.45, where we weighted it so the guy that is more abundant makes up a larger portion of the mass. We did that maybe a couple problems, but I don't think we really tested over that. There's maybe 1 or 2 problems on the homework. So if you want to review that you can go back to the assessment for chapter 2. And then maybe it's this chapter, maybe it's the next chapter, but we learned the difference of ionic versus covalent. We may have learned this in the last chapter, but we may be learning this in the next chapter, but ionic versus covalent. Ionic, remember, you have the full charge. Covalent, you have the shared electrons. Okay. Chapter 3. Chapter 3 is when we get into a bunch of different topics. We get into how do we name our compounds? Naming our compounds. We can go about this several ways. One, when we talked about ionic, we had our ionic compounds. Remember, we could either go for straight up, how do we name it? We could also say, go from structure to name, or name to structure. So if I gave you NaCl, you would know that's sodium chloride. But what does it mean go from name to structure? If I say lead 2 chloride, you have to be able to go lead 2 means it's 2 plus. Chloride is 1 minus. So lead 2 chloride would be PbCl2. So you have to figure out how many chlorides would go with Pb. It wouldn't be PbCl1. That's a wrong answer. PbCl4. That's a wrong answer. You would have to be able to put those together, given the name. Keep in mind, multiple choice. So you're not having to come up with it right off the top of your head. You have to choose from a selection, but you can't be fooled. You have to know at least a little bit to be able to get that down. And then remember the whole idea of transition metals, get the number, the non-transition metals, no number associated. So like sodium, because it's not a transition metal, doesn't get a number. It's just sodium. Because it's in group 1, it's 1 plus. But lead, it's a transition metal, so we have to say lead 2. We talked about bimolecular. So bimolecular was when we had 2 nonmetals. 2 nonmetals. How did we name those? Like dihydrogen monoxide. Like dinitrogen pentoxide, where we used our prefixes to tell how many of each element we used. So don't forget that. And we briefly covered acids and bases. Acids and bases, maybe not as big of a thing. But remember, our acids all ended with acid. Bases, not so easy. But our acids, when we have HCl, it's hydrochloric acid. If it's H2SO4, it's sulfuric acid. But those are pretty giveaway if you... Okay. Also in that chapter was a long chapter. We introduced the concept of moles. Moles, which is our numerical way of counting something. How many atoms of something, except we shrink it down. And when there, we use the molar mass, and we used Avogadro's number. Please note, they will give you any of these constants. They'll give you Avogadro's number. You don't have to memorize Avogadro's number. You need to know how to use it. Avogadro's number is 6.02 times 10 to the 23rd atoms per mole. So we need to be able to use that. So in this chapter, we need to be able to turn moles to grams, grams to moles, moles to atoms, atoms to moles, maybe even grams to atoms. So there you could learn the equations, or you could learn how to use this concept. The equations: mole equals mass over molar mass. You can also do mole equals atoms over Avogadro's number. All those, you could memorize those equations. You could have them and write them down on your scrap sheet of paper the moment you get it. But if you try to memorize all these equations, it's going to be a hard time. What I want you to recognize is molar mass is in units of grams per mole. Avogadro's number is in units of atoms per mole. If we cancel out my previous unit, we know what version to use. This one only turns atoms to moles. What about if you have moles and you need to get atoms? Well, you have to rearrange that equation. And so that means you have to do some extra work. So what I want you to be able to do is be able to recognize it right off the bat. So if I said, just making one up, if I had 25 grams of methane, how many atoms? How many atoms? And they would say the molar mass of methane is 16 grams per mole. And they'd give you this. And you'd have 4 options. So what do you have to do? You would set that 25 grams. The molar mass is grams per mole, so we'd set 16 grams over 1 mole, right there. And then I'd set up, without even missing a beat, Avogadro's number, which is 1 mole, it's 6.02, 10 to the 23rd atoms. I don't have this equation memorized. I would have to actually stop and think for a good 10 seconds to give you the exact equation you need for this. What I'm doing is I'm looking here. Okay, I got that. Then I immediately see, okay, I have moles up there, so I got that. So I know where it's going to go next. So you say 25 divided by 16 times 6 times 10 to the 23rd. That would be whatever your answer is. Don't know what the answer is right off the bat, but that's an example, those type of problems. You could do this. If you can do this, you can answer a lot of the questions for the chapter we're currently on. Now, there's 2 other subjects with chapter 3. Recognizing empirical formula versus molecular formula. We're not going to have to do much with it, but you need to recognize what is the difference between the two. Empirical formula with the simplest whole number ratio of the atoms. If I have CH4, what's the simplest whole number ratio? 1 to 4. Can this be simplified any further? No. If I had a compound that is C2H6, though, is that the simplest whole number ratio? No. We could simplify that. That's equal to CH3. 1 to 3. The molecular formula is the whole number ratio. It is literally what is it. The empirical is the ratio between it. Could I have a different compound that had a ratio of C2H6? of CH3. Yes. Yes, I could have something that was C4H12. That would also have a CH3 compound. They would have the same empirical formula, but they're completely different structures. Be able to recognize empirical formula. And the last thing we went over in that chapter was mass percent. We went over mass percent. Now, what is mass percent? That's mass divided by total mass times 100. Break down what is mass percent. What does that mean to you? If I said my hand weighs 5 pounds and I said I weigh 250, what percentage of my total weight would my hand be? It would be 5 over 250 times 100. The old joke is the only way I'm going to lose weight is if I lose a limb. So how much would I lose? You'd be able to calculate that based on that mass percent. What you're doing is if you're saying, how much of methane is hydrogen? Well, we said the molar mass is 16. Each hydrogen is 1. There's 4 hydrogens, so what is the mass percentage of hydrogen and methane? 4 over 16, which is 1/4 or 25%. So methane is 25% hydrogen by mass. So that is not a big part of the test, but that is something we went over in that chapter. So that's the first 3 chapters. That's the first 3 chapters. So I'm going to erase the board and we'll go on with chapter 4. Chapter 4 is the property of light chapter. Though property of light was not the only thing we went over. Property of light is actually the smallest part of that chapter. So we may have spent a lot of time on the property of light at the very beginning. The property of light is not a big portion on the test. But we did go, chapter 4, we looked at the properties of light, electromagnetic radiation, which involved 2 equations, E equals H nu, and C equals lambda nu. The wavelength times the frequency equals the speed of light, and the frequency times the Planck's constant would be the energy that light contains. Now, this may be 1, maybe 2 questions on an exam. It's not a very big point. Out of 70, you might be able to get this by guessing. You might know enough that it's an easy question, but don't spend a ton of time memorizing these equations. Nothing else. But so let's look at this real quick. Energy, literally this one is the easiest one. You have a constant, it will be given. If you have a frequency, you multiply those 2 together, you'd get joules. The harder one is this guy, where you have to take C over lambda equals nu, or C over nu equals lambda. And oftentimes we're going to go from meters to nanometers, or from nanometers to meters before we can plug that in. That's why I said you need to know the conversion, because oftentimes wavelengths of light are not set in meters. If they're in meters, we're talking about like radio waves or television waves. So those are not waves we deal with very often. Okay. Now, the big part of chapter 4 involved the quantum model of the atom. We learned some weird ways of designating this, but we learned about our orbitals. We said, oh, we have the S, we had the S, the P, the D. We recognized we would have one S, then two S, then two P, and then 3S, and then 3P, then 4S, 3D, 4P. We represented them. This first number was our N. Our second letter designation was our L. We didn't really talk about this too much, mainly because this is confusing as all hell. But then these degenerate orbitals were our M sub L. And then our spin state was our M sub S. But those were different ways of describing each and every electron in here. We can pair these up. Hopefully you remember those box designations and say, what element is this? Well, it's 1s2, 2s2, 2p3. 2p3 puts us at nitrogen. How would we describe this electron? That would have been N is 2, L is 1, and then like M sub L is positive 1. But the one thing we did was like N is any number, L is always equal to, can go up to N minus 1, and M sub L is anywhere from negative L to positive L. We didn't really talk about this too much. It's not a huge part, but is how we recognize that. The more important thing here is you recognize the box notation. You recognize how to do the electron configuration. You can either go from the atom to the electron configuration or the electron configuration to the atom. Recognize the difference between full and condensed. Probably more often condensed electron configuration. Full, remember, we just use all of it and we work our way across. Or condensed electron configuration is where we look at what row our element is in, and then we use the noble gas from the row above it. So if I say bromine, the noble gas for the row above it would be argon. I would say argon, 4s2, 3d10, 4p5 for bromine. So you got to do that. The reason I emphasize this, because some people screwed this up bigly on the last test when they took this. They confused condensed with full, and I don't want to make the same mistake where we can help it. Another thing, be able to recognize neutral versus charged. Charged. How would we do the charged electron configuration? You look at what is the charge. If it's positive, we subtract electrons. If it's negative, we add electrons. But charge, we remove electrons. We remove electrons from the P, then the S, before the D. We would touch the D last. So if I said bromine, +7, I would remove all 5 of the P, all 2 of the S, and bromine +7 would have electron configuration of 3d10. There would be no 4p, there'd be no 4s. I would remove the P and the S. The most common one you might see would be lead-4. Lead-4 would be what, like, that's row 6. You would lose the 6p. You would lose the 6s. and you would have a completely filled 5D and a completely filled 4F. We would not touch those guys. So be able to do that. Be able to do that. If you know how to do electron configuration and all its little tricks, that's 2, 3, 4 questions you could easily do. Said property of light, that's 1, maybe 2 questions. You do electron configuration, well, that's 3, 4 questions. You're looking at a better use of your time and hopefully something that is less persnickety. That was chapter 4. Chapter 5, we talked all about the properties. All about the properties. So chapter 5, we looked at the properties of our elements, reading off the periodic table. Properties. We looked at Z effective. I'll go through these properties again once I write them all down. We went through atom size. We went through ionization energy. And we went through electron affinity. Those were our big properties. So Z effective was what effective charge did the valence electrons see from the nucleus? Z effective was the highest on the upper right. So helium had the highest. So francium would be the lowest. It's essentially, as we moved across the periodic table, we saw the Z effective go up. As we moved down the periodic table, the Z effective essentially went up very, very slightly. So as we get further and further from the nucleus, the big thing is we move across the table. Now, atom size. Atom size had to do with the Z effective. So it went cesium, well, let's say francium was the biggest. Helium, smallest. That's because as we move down the table, we added layers and layers and layers of electrons. We added a layer of clothing, essentially, that made it bigger and bigger. As we moved across the table, the Z effective went up, which pulled everything in. And then we also could talk about charge. Losing electrons shrinks. Gaining electrons grows. So if I compared O2 minus to F1 minus to neon, O2 minus, despite being to the left of neon, is bigger than neon. F minus, despite being the left of neon, is bigger than neon. Because the bigger the number of electrons means it's a bigger element. It's like when we add an electron, we're like gaining 10 pounds. Well, if you gain 10 pounds, you're going to be bigger. Whether muscle or fat, you're going to be bigger. You lose some electrons, you're losing some weight. You're going to shrink down. Maybe you fit in a different pant size. Ionization energy. Ionization energy, it's highest on the upper right. This was your losing energy to lose electrons. The easier it is to pull away the electrons, the lower the ionization energy. We could look at this in just terms of first ionization energy, but we can also look at this as multiple ionizations. So, completing row. Let me put it like this. Removal of last S electron sees big jump in energy. So remember, I think we did one of these on the test. We did one of these on the homework. That if I said losing 1 electron, 2 electrons, 3 electrons, you see a gradual increase, and then 4 electrons, an increase of like say 10,000, as opposed to an increase of like 2,000. You know, well, that guy must have 3 valence electrons. What element could that be? Well, that could be boron, that could be aluminum, that could be gallium. It's not going to be carbon. It's not going to be silicon. So you can use the ionization energies to determine what column it's in. Electron affinity. Electron affinity is the energy to gain electrons. And once again, up right in the fluorine highest. Guys who don't need electrons will have low energy that they get from it. Guys in the upper right quadrant will have the highest. Fluorine, oxygen, and neon. Easy ones to remember. The top 3 are going to gain the most energy. But along those lines, we learned bond polarity. Bond polarity. How did we do that? You got to spell that polarity. My vowels shifted over one. Bond polarity, where you compare the electron affinity of and electron negativity of various elements. You may not be given actual numbers, but you'll look. If it's in those top 3, there's nitrogen, oxygen, and fluorine, and it's with a different element, it's probably pretty polar. If it's one of those middle elements, it's probably not very polar. If I said silicon and carbon, not very polar. But if I say silicon and fluorine, ooh, that's probably polar. And then finally, we briefly looked at lattice energy. Lattice energy. The energy of our ionic bonds. That was proportional to the charge and size. We want big charge, small size. So if I compared beryllium fluoride with lithium fluoride, which of those guys would have more lattice energy? Beryllium, because beryllium is 2+. If I said beryllium fluoride versus beryllium oxide, which one is more lattice energy? Beryllium oxide, because we have 2+ and 2-. So just comparing those, if you look at the charge is almost always everything. But that is a small portion, if anything. If you can get the trends are probably a bigger portion of the test. That was a bigger portion of the chapter. But the trends is still only like, I don't know, 4, maybe 5 questions. Okay, let's see how we're doing on time. Let's see. 45. Oof. So let's see. I'm going to go ahead and call it there. I'm going to briefly talk for a little bit more, but I'm not going to go into chapter 6 yet. We will hit up chapter 6, 7, 8, 9. Well, no, we'll try to get partway through 6. We'll see how far we get. Because otherwise, the other stuff has a lot of math. We got a little bit of time. So, chapter 6. The big thing we learned there is all about Lewis structures. So how are we going to have to answer stuff about Lewis structures? We're not going to have to actually draw anything. It will either be drawn for us, or we might have to sketch it on a paper and answer a question about it. So remember, this was a big Lewis structures and covalent bonds. Structures and covalent. What is a covalent bond? Covalent bond is shared electrons. Covalent bonds. But so, what could we be asked about Lewis structures? We could be asked about, say, how many bonding electrons, how many bonds, or how many non-bonding lone pairs. So if I gave you a Lewis structure with no lone pairs on it, could you put the lone pairs, the missing electrons? Could you put those on there? We could also be asked about octet rule. Does this guy fit the octet rule? And we can be asked about formal charges. Formal charges. How did we do the formal charges? Remember, formal charges were when we compare expected valence electrons to actual Lewis electrons. So if oxygen is expected to have 6 valence electrons around it, and I see 7 valence electrons around it, or 7 valence electrons around it, what is the formal charge? It would be 1 minus. If I see 5 valence electrons around it, it's 1 plus. So the formal charge depends on the expected number versus actual. We could be asked about resonance structures. Resonance structures. That essentially, these different structures that all are the same thing, but they come when the electrons are swapping. The electrons move to get it between structure A to structure B to structure C. The electrons are shifting around. See, you could easily look at bond length versus strength. As we get more bonds, the bonds get shorter, but they get stronger. And then we could look very briefly at bond dissociation energy. This, in the book itself, this is actually put in the last chapter, chapter 10. But I like to introduce it in chapter 6 because this is when we start to do Lewis structures. But it's the energy. The bond dissociation energy is, the energy is equal to bonds broken minus bonds formed. Why is it? This is going to be reactants minus products. This is actually directly opposite of what we do in chapter 10. Why do we do this? Because bonds cost energy to break. To break, bonds give energy when made. When made. So if I have to chop some bonds apart, I have to use some of that energy. And then we're measuring and subtracting out the energy we get back when they snap together again. And so in order to get energy produced, the bonds formed must give more energy than what costs to break the bonds in the first place. But how would you do that? You would look at all the bond types, add up all the bonds broken, look at all the bonds types, add up all the bonds formed, and subtract the two. We'll maybe do a problem on Wednesday of this. It's not a huge part of the test, but it's a very easy thing if you're fresh in your mind. How do we do enthalpy? That is actually all the stuff for chapter 6. All the stuff for chapter 6. It's mostly about Lewis structures. How do we recognize a valid Lewis structure? How do we put charges on valid Lewis structure? How do we put electrons around a valid Lewis structure? There's not much more we can do with that. What might be more of a troublesome part is the next chapter, which is the VSEPR models. But we'll go into that, as I said, on Wednesday and continue. Thank you, and I will see you guys on Wednesday.